Right now, while you're watching this, something is happening 15 billion miles from Earth that almost nobody knows about. A machine the size of a small car is moving through a part of the universe where no human being has ever looked before. It was built before the internet existed. It runs on less power than the light bulb in your bathroom. And this ancient, tiny spacecraft that was only supposed to last 5 years is sending us information that is forcing physicists to rewrite what they thought they knew about the edge of our solar system. This is not speculation. This is not theory. NASA confirmed it 3 months ago, and the implications are still rippling through the scientific community. The researchers studying the data are not using words like interesting or unusual. They are using words like baffling, and we were completely wrong. This is the story of Voyager 1 and what it just found in interstellar space. By the time this video ends, you will understand why this discovery matters, not just to scientists, but to the long-term survival of everything alive on Earth. If you want space content that treats you like an intelligent adult, subscribe to Space Horizon right now. We cover the discoveries that actually matter. Explain the way working scientists talk about them. Let us begin. September 5th, 1977. A rocket lifts off from Kennedy Space Center carrying a spacecraft called Voyager 1. The mission plan is straightforward. Fly past Jupiter, fly past Saturn, take photographs, collect measurements, then drift into deep space and go silent. Expected lifespan is 4, maybe 5 years. NASA engineers plan to celebrate the mission ending sometime around 1981. What actually happened became one of the most extraordinary achievements in the history of human exploration. Voyager 1 did not go quiet. It flew past Jupiter in March 1979 and sent back the first detailed images of that planet's atmosphere that human eyes had ever seen. It passed Saturn in November 1980, capturing images of the rings that revolutionized our understanding of how planetary ring systems form and behave. Then it kept going, using the gravity of each planet like a slingshot, adding speed with every encounter. By the time the 1980s ended, Voyager 1 had already traveled farther from Earth than any object humans had ever built, and it was still transmitting, still sending data, still functioning on hardware that modern engineers look at with a mixture of admiration and disbelief because nothing built today could survive what Voyager 1 has endured. Then, in August 2012, 35 years after launch, something happened that changed the entire story. Voyager 1 crossed the heliopause. If you have never heard that word before, it is the single most important boundary in our cosmic neighborhood. Here is what it means. The sun does not just give us heat and light. It constantly releases a stream of charged particles called the solar wind. This wind blows outward in all directions, forming a protective bubble around our entire solar system. That bubble contains every planet, every moon, every asteroid, every comet, and every living thing that has ever existed. The outer edge of that bubble, where the solar wind finally loses its energy and gets stopped by the pressure of interstellar space pushing inward from the other side, is called the heliopause. Everything inside that boundary is part of our solar system. Everything outside is interstellar space, the actual space between stars. On August 25th, 2012, Voyager 1 became the first human-made object to cross that line. It left the solar system and entered the space that lies between star systems, a region no telescope on Earth can observe from the inside because we have never had an instrument there before. And then it kept transmitting. Think about what that means. We have, right now in 2026, a functioning scientific instrument sitting in interstellar space, sending back direct measurements of an environment that every scientific model describing that region was built without ever having real data from inside it. For decades, scientists used mathematics and theory and observations from Earth to predict what interstellar space should look like. They built detailed models describing the density of plasma out there, the temperature, the behavior of magnetic fields. Those models were reviewed, published, tested, and accepted. Voyager 1 walked into that space and discovered the models were wrong. Starting in 2017, the plasma wave instrument on board Voyager 1 began detecting something nobody expected, a persistent low-frequency hum in the interstellar plasma. Not a burst, not a temporary spike that could be dismissed as an instrument glitch. A continuous emission detected year after year across more than 900 million miles of space. To put that distance in perspective, the space between Earth and the Sun is 93 million miles. The signal has been measured across a region of interstellar space more than 10 times that distance. Scientists publishing their analysis in the journal Nature Astronomy were direct in their conclusion. Interstellar space is not the quiet, smooth environment the models predicted. It has structure. It has turbulence. It is far more complex and dynamic than any theory built from Earth had accounted for. Now here is where this stops being abstract and starts affecting you personally. The same bubble that separates our solar system from turbulent interstellar space is the bubble that protects life on Earth. The heliopause is not just a line on a diagram. It is a shield. It deflects the most dangerous cosmic radiation, high-energy particles streaming in from distant exploded stars from reaching the inner solar system at full strength. If that shield is weaker or more unpredictable than models suggest, the implications for every living thing on this planet are significant. And what Voyager 1 is telling us is that the interstellar environment pressing against that shield from the outside is more energetic, more variable, and more structured than any model built before we had real data. We do not yet know exactly what that means for the long-term stability of the shield itself, but the fact that we now have to ask that question is itself a fundamental shift in how we understand our own cosmic vulnerability. Now the story gets more complicated, because in 2023, Voyager 1 nearly died. For 5 months, the spacecraft continued transmitting a signal back to Earth, but the data it was sending was unreadable. Corrupted code, scrambled information that engineers at NASA Jet Propulsion Laboratory, after decades of successfully operating this mission, could not decode. The spacecraft was alive, the signal was coming through, but whatever it was trying to tell us had become gibberish. The problem, when they finally identified it, was both simple and devastating. A single memory chip inside the flight data system had failed after 46 years of constant exposure to cosmic radiation. One tiny piece of 1970s hardware measuring a fraction of an inch had developed a fault that corrupted the software responsible for packaging and transmitting scientific data. In a normal engineering situation, you fix a broken component by replacing it. In this situation, the broken component was 15 billion miles away. The only available tool was radio signals traveling at the speed of light, and even those signals took 22.5 hours one way to reach the spacecraft. Every single diagnostic test, every attempt to understand the problem, every potential solution required a minimum 45-hour round trip just to see if it worked. Think about the pressure of that engineering process. You form a hypothesis about what might be wrong. You write a set of instructions to test it. You transmit those instructions. You wait 22.5 hours. You receive the response. You analyze what came back. You discover something slightly different from what you expected. You form a new hypothesis. You write new instructions. You transmit them. You wait another 22.5 hours. And you do this for months, knowing that one wrong command sent across 15 billion miles of space could permanently end the mission with no possibility of recovery. The team at JPL worked through this process, step by careful step. And in mid-2024, they succeeded. They could not repair the corrupted memory, but they found a way to relocate the affected software to different parts of the spacecraft available storage. Each section was individually rewritten to work from its new location, then carefully reconnected to function as a whole system. It was remote brain surgery performed through a 45-hour time delay on a 47-year-old machine sitting farther from Earth than anything humans have ever touched. Voyager 1 came back online. It resumed transmitting clean, readable scientific data, and what it immediately started sending back was more evidence of those unexpected plasma oscillations, more measurements of structure and turbulence in interstellar space that the models had never predicted. But here's the discovery that NASA confirmed just 3 months ago, and this is the part that genuinely shocked researchers who have been studying the heliopause for decades. When Voyager 1 first crossed the heliopause back in 2012, scientists expected the transition to be gradual. The solar wind thinning out slowly, the interstellar medium gradually becoming detectable, a smooth blending at the boundary like a river slowly meeting the ocean. That is not what Voyager 1 found. At the heliopause, the charged particles were not gently mixing. They were colliding at speeds approaching a significant fraction of the speed of light. The energy from those collisions was generating temperatures exceeding 3,000 degrees Celsius, not inside a star, at the edge of our solar system in what was supposed to be cold, relatively empty transitional space. Some researchers have described this region as a wall of fire, and that is not a metaphor. It is a genuine concentration of ultra-high energy particles forming a physical barrier at the boundary of everything we call home. NASA scientists presenting this data at the American Geophysical Union Conference in December 2025 were careful with their language, but the implication was clear. The boundary between our solar system and the galaxy is far more violent and energetic than any pre-Voyager model had predicted. Then came the magnetic field discovery, and this is where the story becomes even stranger. For decades, one of the core predictions about the heliopause was that magnetic fields on either side of it would be completely separate. Inside the bubble, the sun's magnetic field. Outside the bubble, the galaxy's magnetic field. Two distinct systems with a clear division at the boundary. Voyager 1 found something entirely different. The magnetic field lines from the sun, carried outward by the solar wind, do not stop cleanly at the heliopause. They interact with the galactic magnetic field outside through a process called magnetic reconnection. Field lines from different sources merge, rearrange, and release energy in the process. What this means is that the solar system and the galaxy are not magnetically isolated from each other. They are connected. Energy is being exchanged at the boundary in ways that no model built before Voyager 1 crossed that line had accounted for. If the relationship between our solar system and the surrounding interstellar environment is more dynamic and more connected than we thought, then our understanding of how the heliosphere protects Earth needs to be reconsidered from the ground up. Now let us talk about what is happening right now in 2026, because Voyager 1 is running out of time. Earlier this year, NASA made a decision nobody on the mission team wanted to make. The low-energy charged particle experiment, one of Voyager 1's scientific instruments that had been collecting data almost continuously since 1977, was switched off. Not because it stopped working, it was functioning perfectly. It was shut down because there was not enough power left to keep it running. Voyager 1 gets its electricity from 3 radioisotope thermoelectric generators. These devices contain plutonium-238, which produces heat as it slowly decays. That heat gets converted into electricity. At launch in 1977, the generators produced about 470 watts of power. Today, nearly 49 years later, they produce roughly 250 watts. They lose approximately 4 watts every year. At some point in the early 2030s, the power output will drop below the minimum level needed to run any instrument at all. When that happens, Voyager 1 will go permanently silent. The team has known this was coming for years. They have been carefully planning which instruments to shut off and in what order to extract as much science as possible from the dwindling power supply. Of the 10 instrument packages Voyager 1 carried at launch, 7 have already been turned off. But here is something most people do not know. The engineers have not given up on getting more time. They are currently testing what they have internally called the Big Bang procedure. It is an experimental attempt to restructure how power is distributed across Voyager's remaining systems to extract additional capacity from components currently running at lower efficiency. The procedure carries real risk. Even small changes to power flow through a nearly 50-year-old spacecraft with no manual override could cause failures. So the team is doing what careful engineers do. They tested it first on Voyager 2, which has slightly more available power and is closer to Earth, making a potential problem less catastrophic. Those tests happened in May and June of this year. If the results show it is safe, the same procedure will be attempted on Voyager 1 as early as this summer. If it works, there is a real possibility that the instrument they just shut down could be turned back on. The team is not making promises, but they are still trying. Because with Voyager 1, assuming something is finished before it actually is, has never once been the right assumption. And now comes the moment that is already locked into the calendar. On November 18th, 2026, at 2:16 in the morning, Pacific Time Voyager 1 will reach a distance of exactly 1 light day from Earth. That means it will be so far away that light itself, the fastest thing in the universe, takes exactly 24 hours to reach it. If you send a command to Voyager 1 on Monday morning, you will not know if it arrived until Tuesday morning. You will not get the spacecraft's response until Wednesday morning. No human-made object has ever been that far from home. On that date in November, Voyager 1 will cross that threshold while it is still alive, still transmitting, still sending back data, and then it will keep going. Every hour, Voyager 1 travels another 38,000 miles deeper into interstellar space. The communication delay grows longer, the power supply shrinks, and at some point in the 2030s, the last signal will arrive on Earth. After that, there will be nothing. But even then, Voyager 1 does not stop. There is nothing in interstellar space to stop it. No friction, no atmosphere, no gravity well strong enough to pull it off course. It will keep moving silently in a straight line at 38,000 miles per hour into a darkness that has no end on any human timescale. And attached to its frame, bolted to the side of this dying machine, is something that will outlast everything. The Voyager Golden Record, a gold-plated copper disc carrying greetings in 55 human languages. The sound of rain, ocean waves, human laughter. 90 minutes of music from cultures across human history, diagrams explaining our mathematics and physics, and a map showing the location of our sun using the positions of 14 pulsars as reference points. Carl Sagan, who helped design the record, called it a message in a bottle cast into the cosmic ocean. That is exactly what it is. Whoever finds it, whether that is another civilization a million years from now or something we cannot currently imagine, will know that we were here, that we were curious, that we built something from metal and electricity and launched it beyond everything we had ever known, carrying the sound of our own voices. The record will still be traveling when the sun expands into a red giant and consumes the Earth. It will still be moving when every city we have built and every monument we have carved has been erased by time. It is the most permanent thing our species has ever created, and it is riding on a spacecraft that runs on less power than your microwave. Here's what I want you to take away from this. Right now, in 2026, the only functioning scientific instrument humanity has ever placed in interstellar space is 48 years old. It was built with 1970s technology. It is powered by 250 watts of electricity. And it is sending back information that is changing our understanding of where the solar system ends and how the boundary between our home and the rest of the galaxy actually works. We have built things that are larger. We have built things that are more expensive. We have built things using far more advanced technology. But none of those things are telling us what Voyager 1 is telling us right now. Because none of them had the one quality that mattered most. None of them kept going long enough to get there. The data Voyager 1 is sending back about plasma density in interstellar space, about the structure and energy at the heliopause, about magnetic connections between the solar system and the galaxy cannot be gathered any other way. You cannot get this information from a telescope on Earth. You cannot infer it from models. You can only get it from a machine that actually crossed into interstellar space and survived long enough to tell us what it found. We have exactly one such machine. It is old. It is dying. It runs on the power equivalent of 3 light bulbs. And as long as it is still transmitting, we need to be listening. Because when the signal stops, the answers to some of the most important questions we have ever asked about our place in the universe will go quiet with it, at least for a generation. If this is the kind of space content you come here for, subscribe to Space Horizon and turn on notifications because we are going deeper next time. Leave a comment telling me what surprised you most about Voyager 1's story, and share this with someone who still believes humanity is capable of extraordinary things. The signal is still coming, stretched across 15 billion miles, delayed by 22.5 hours of travel time, carrying information about a universe that is stranger and more connected than we ever imagined. One machine, 4 watts of declining power, one chance to listen before the silence comes. Thanks for watching Space Horizon. We will see you in the next one.